Hello students. So let's try to solve one more problem from JEST 2021, and this problem belongs to the special theory of relativity, mainly Doppler effect. It's a wonderful problem, and this problem is from part C and question number 10. And obviously the set is D set. So what is question? Question is that there is two stars which are rotating in a circle about its common center of mass. So, and both have mass m, both have same mass. So obviously if both have same mass and they are moving about its center of mass, then obviously these two star will always make their diametrically opposite situation. Then only they will move along the circle, and where center will be the center of mass of the composite system. Means suppose one star is here, then another star will surely there. Suppose one star is here, then another star is there. So this situation will be maintained always. Then only it will move, about a center of mass. Okay, because both have mass m, so it's a very easy to find center of mass will be just center of this particular uh, center of the circle or circular orbit. And in this problem, it is given that a ratio between, and they are emitting light, so they are also emitting lights, and the observer is, and the main thing is that the axis of a plane of rotation is perpendicular to line of sight. So this is very important thing. So what will happen? So this is the axis of rotation, and the observer may be in this particular situation because he is perpendicular to this line of axis of rotation. So suppose something is rotating like this and another star is rotating like this. Suppose first star is here, the second star is here. Suppose it is rotating like this, then this will be rotating like this. Suppose first star is here, then this will be rotating like this. So this is axis of rotation. So this is axis of rotation, and these two stars are rotating something like this. And I can assume that at this particular point there is observer, the point of sight. So this observer will find the ratio between the maximum wavelength of the light to the minimum wavelength of the light, and that is given as something 1.0022. So lambda maximum by lambda minimum is equal to 1.0022. So this is given, as well as the time period of this star is also given. So time period is given as 2.40 into 10 to the power 5 seconds. So it's a very fast. So we have to see what will be the condition when this observer will see the maximum and minimum wavelength. So in the term of frequency, if suppose first we will talk about frequency, then obviously inverse will be all about its wavelength. So suppose if this is moving like this, suppose it is moving in this direction, so velocity is in this direction, and light pulse is coming in this direction for this observer. So this will be the situation for the minimum frequency or maximum wavelength. So what will be maximum wavelength? So maximum wavelength is equal to, given as some lambda naught 1 plus V upon C upon 1 minus V upon C. So this is lambda max, and we are using the concept of Doppler effect for the light because they are emitting the light. So when this is situation for first one, then second one have situation, the light is coming here and this is coming in this direction. So this will be condition for minimum wavelength. So this will be condition of minimum wavelength, and this will be 1 minus V upon C, 1 plus V upon C. Obviously in term of frequency, this will be condition of minimum frequency and this will be condition of maximum frequency. And if you want to see this point and this point, here light is coming in this direction, velocity is in this direction, so this is the perpendicular thing, and it is obviously not minimum and maximum. We have done this all thing in our class. Okay, So let's try to, now we have to just go for all our calculations. So when I have done this calculation. So we have lambda maximum by lambda minimum. We can just take this particular thing. Lambda naught is the frequency when the star is rest. So we can see the original frequency lambda naught. So when we are going to calculate this thing, then this value is 1 plus v upon c upon 1 minus v upon c, and this value is given 1.002. So we can calculate this value, and this value is very small, and that is 0.00109 c. So this is very small, but obviously we have to write in term of c because we are talking about the light pulse. So, but this is the velocity of a star, which is very small. It is also given that it is very small, but even if it is given very small, we have to use the Doppler effect of a light. You cannot go for the Doppler effect of a sound. So you have to use this formula for the Doppler effect. Okay. And this is my velocity, and we also know v is equal to omega r. V is equal to omega r. So, and omega is also given. So omega is equal to what? 2 pi upon t, and this is r. So when we will put the value here v and t is given, then we can easily calculate the value of r. So value of r will be come to 12.5 into 10 to the power 9 meter. But we have to find the distance between these two stars. So this is the question. So at the every position, hence these two masses, suppose its mass is m, its mass is m, suppose these two masses will always make the diametrically opposite situation. So we have to actually calculate the distance between these two is nothing but 2r, and this 2r is equal to 2 into 12.5 into 10 to the power 9 meter, and that value is 25 into 10 to the power 9 meter. So answer is equal to, so obviously we have to give the answer into 4 digit, so that value is equal to 0025. It's a wonderful question. It's a wonderful question. Lot of people are confused by v upon c tends to 0. No, don't confuse it. Calculate it properly, because you have to talk about the light. So you have to use the Doppler effect of light. Don't confuse with the Doppler effect of sound. So this is very nice question and nice solution. And I will give you the special thanks to my colleague Mukaddar, who has solved this problem in a very nice way. Thank you.